All right, we are moving on to 6.2. We are still in chapter 6, looking at identities, thinking about identities and how we're going to get closer and closer to these equations in order to solve equations in chapter 6. All right, we're going to be looking at 6.2, something called the sum and difference formulas. And particularly, we're going to look at the sum and difference formulas for cosine first. And then we're going to revisit this whole cofunction theorem, cofunction identities. I know we did that in chapter 5, I believe. But now we'll do that in chapter 6. And then again, the sum and difference identities for sine, sum and difference identities for tangent. So before we go on, I guess the question is, what in the world why do we even need to look at the sum and difference identities? So let's kind of quickly here, before we go on to the formulas themselves here. What we want to do is this whole concept is do you know the value of cosine of 45 degrees? And you can say, yes, Mr. H, we know it. It's square root of 2 over 2. That's easy enough here. And we do know how about this cosine value of 30 degrees? Do you know what that is? All right, yes, Mr. H, square root of 3 over 2. Okay. Now, we know multiples of 30 and we know multiples of 45. Those are the two multiples that we know, or those degrees and any multiples thereof. The question is, we want to, in a sense, push the envelope. We want to say to ourselves, is there any which way to know any more exact values or exact ratios, particularly of cosine maybe, that is not a multiple of 30 or multiple of 45? For instance, can I maybe somehow get the exact value of cosine of 75 degrees? Is there a way to do that? And that's what these sum formulas are, because if you think about it, isn't 75 degrees really just 45 degrees plus 30 degrees? Or the other way, 30 degrees plus 45 degrees. And there it is. This is the sum formula. It's exactly what I want. I want to develop some formulas that I can add an angle measurement together and still get the exact values of them. All right, so for cosine, if I'm going to add two angles together, like I did the 45 and the 30, this is our formula. It looks kind of weird at first. It's actually some multiplication here. What we do is we take the cosine value of the first angle, cosine value of the second angle value, then we subtract the sine values. It's kind of interesting. Again, that's the way the formula is given here. Cosine, again, if you're going to be subtracting, what we do is you take the cosine values of each of the angles and you add the sine values of each of the angles. Again, we could go into a proof on it, and we just don't have time to do so. But let's take a look at an example. How's this used? All right, so let's go for it here. So the exact value of, we want to know the exact value of cosine of pi over 12. And on the homework, it does give you a little help here. It says use pi over 3, subtract pi over 4 to get you pi over 12. And if you do that, you can check this if you like. Go ahead and get common denominators of 12 and see if this actually is true. I think it should be, because if this is a 12, this would be a 4 pi on top. This 12 would be a 3, and 4 pi minus 3 pi is just a regular pi. All right, let's go for it here. So how's this used at? We're going to find the exact value of cosine of pi over 12. What we do is we can use the measurement of the angle that's given. So now we're going to do a subtraction between two angles to give you the same value. And then we plug into the formula that we saw on the previous slide. We get the angles, the trig functions of the angles we already know. Simplify, and we are done. So there it is. Now I have a exact value of a angle measurement that's not a multiple of 30 or a multiple of 45. All right, also, these things will come up a lot. You'll see a square root of 2, you'll see a square root of 6, you'll see a 4 come up quite a bit. All right, practice problem. For us, the practical problem is cosine of 15 degrees. Can you figure out the exact value of cosine of 15 degrees? And it tells you how to do that here. Let's take 45 degrees, subtract 30 degrees. Again, these two angles have to be angles that we already know about. All right, so let's go for it here. So cosine 15 degrees, split it off. It's going to be now cosine of 45 degrees minus 30 degrees. And we plug into a formula. Give you guys a little bit of time to plug into a formula. All right, here's what I got. I got cosine of 45 degrees times cosine of 30 plus, remember according to the formula, there's always a change in sign over here, sine of 45 degrees, sine of 30. All right, if you have not done so already, evaluate each of those, simplify, and you should be done. So cosine of 45 degrees, root 2 over 2. Cosine of 30 degrees should be root 3 over 2. Cosine of 45 degrees, root 2 over 2. And sine of 30 degrees is 1/2. So it should look like this and that. Simplifying each of those and eventually simplifying to the end gives us that. All right, if you do look at the previous slide or the example problem that's given, notice that these two answers are exactly the same. The reason for it is technically because if you look at pi over 12 from the previous slide and you change it to degrees, so remember 180 degrees over pi, and you do something like this, and you take half of that would be 90, half of that would be 6, half again because they're both even, 45 degrees over 3, and then 45 divided by 3, it would give you 15 degrees. So really, cosine of pi over 12 is really the same thing as cosine of 15 degrees. That's why the answers are exactly the same. All right, now slightly a little different here. How about 7 pi over 12? All right, this one I do want to verify that pi over 3 plus pi over 4 will actually give me 7 pi over 12. So just to show. So, I want to show all the different sort of equivalent forms just so you guys can see it later here. So remember, pi over 6 is very important, pi over 4 is important, pi over 3, pi over 2. Those are the important values that we have used so far. 0 also important because we've used it as well. But if you're doing this and the homework does not tell you which angles to use, what you'll have to do is you have to just get common denominators for each of those and then look at the denominator that you're using here. So pi over 6, if you change it to a denominator of 12, would be 2 pi over 12. Pi over 4 then becomes 3 pi over 12. Pi over 3, 4 pi over 12. And pi over 2 makes us 6 pi over 12. Okay, which one of those, if added together, would give you 7 pi over 12? It's this little the middle 2 right here. Because 3 pi over 12 and plus 4 pi over 12 will give you 7 pi over 12. Therefore, we're going to use pi over 4 and pi over 3. So if you ever try to find it yourself, there you go. Okay, let's go for it though. So cosine of 7 pi over 12. We're going to break that up into cosine of pi over 3 plus pi over 4. And again, use the formula. Give you guys a little bit of time to get ahead of me. Go for it if you need be. All right, the formula given there, cosine of pi over 3 times cosine of pi over 4, subtract this time because the formula, sine of pi over 3, sine of pi over 4. Again, you should be able to get these values really quick right away here. So 1/2 times root 2 over 2, subtract root 3 over 2 times root 2 over 2. Simplifying, finishing it up, and you got yourself root 2 minus root 6 All that divided by 4. Notice that root 2, root 6, and that 4 keep coming up quite a bit. They will come up on the homework as well. Alright, so my question is, what is the angle measurement that I just figured out? Cosine of 7 pi over 12, what is that? So if I go and convert this to angle measurements in terms of degrees here, so pi over 3 really is 60 degrees. Pi over 4 is 45 degrees. So if I were to add these up, 60 plus 45 is 105. So I just figured out the exact value of cosine of 105 degrees. And that's cool. All right, in the last chapter, I think we remember something called, I think it was called the cofunction theorem. The cofunction theorem just stated that if you're trying to figure out the sine of, let's say, 48 degrees, it's really the exact same thing as cosine of its complement. Remember that, so because 48 plus 42 would give you 90 degrees. Or something like this here. So sine of 50 would be the exact same equivalent of sine of 40. That was in chapter 5. If you want to, you can punch in a calculator. You can say sine of 50 degrees, click. Then you say cosine of 40 degrees, click, enter, and those values should be exactly the same. So how is it stated? It's stated like this. It's stated as sine of 90 degrees minus x is equal to cosine of x. Or you just swap the identities here. Alright. So really what this says is that sine and cosine, there's a 90-degree difference between them two as well. So if you want to convert this to radian measurement, you can also convert to radian measurement by saying cosine of pi over 2 minus x is equal to sine of x. So again, basic cofunction identities. This is really just from chapter 5. We looked at these in chapter 5. What we want to do now in chapter 6 is to prove them, to prove that is actually true. And so let's go for it here, now that we have the sum and difference formulas. Alright, so proving it for tangent. Let's see if this is true. Tangent is, again, the complementary angle of tangent is the same thing as the cotangent of that angle. And we can prove it for tangent. We say tangent of complementary angle would be, again, this is just basic identities, right? Tangent is sine over cosine. And given those basic cofunction identities that we just saw in the last slide, gives us this, therefore we're left with cotangent. Alright, can you prove this here? Give you guys a little bit of time. Can you start off with secant and prove that secant is really the cofunction for cosecant? Or you can say it the other way here. You can say that the cosecant function is really the cofunction of secant. Alright, let's go for it here. So on this side, I should have moved that a little bit further out here. Move that like this. Tell me if you guys agree here. Secant, I got to figure this out. I got to make it either go to sine or to cosine. One of them I got to do. So for secant, I'm going to change it to cosine. Again, it's the reciprocal identity. On the other side, I can also simplify that side as well. Cosecant is really 1 over sine. And then you say, well, those are actually exactly the same by the cofunction identity. So cosine of pi over 2 minus x is really just going to be sine of x. And I have just proved it. In the olden days, what you had to do is you had to go from one function to another here. So in a sense, what you would do is you start off with the, again, right-hand side, the more complicated side. simplify it out to cosine or sine, use the cofunction theorem, and then bring it back to the right hand side. If you did that, you technically were done, because you've proved by equal signs running all the way across, those two are the same. In the old days, what you would do when you finished with the whole entire problem, you would write something called QED. And I'll let you guys try to figure out what in the world is QED. You can probably just Google it or something, look it up. But up until about the 1970s, all the trigonometric books, all the trigonometry books had QED as their abbreviation, that you've completed the identity. Alright, we also have the sine and sum and difference formulas for sine. And so those run like this. Again, these probably should go in a 3x5 card somewhere. That'll be a good idea to have them there. Alright, and of course we're going to start proving some identities. So practice problem number 4 is, can you prove this identity that sine of pi plus x is going to be the negative of sine of x? If you add pi to any angle for sine, it will be the exact opposite of for sine of that angle. And again, you can use the sum or difference identities here. Alright, because it's sine of pi plus x, we might as well write down the formula for the sum, the formula for sine. Alright, using pi as our first angle, using x as our second angle. And if you want to, you can go back over here on the unit circle. And really what you're saying is this. You're saying, if I have sine of x, let's say it's right over here. Now whatever the value here is. Let's say it's like 30 degrees here. And then what I do is I add exactly pi, exactly 180 degrees. And the question for it is it going to give me the exact opposite of the y value? It sure will, because now you're in quadrant 3. Now both of them are opposites. And notice that 1/2 initially for the y value now becomes a negative 1/2 for the y value now. Okay, that's just one problem to say, yeah, it works at least for this problem. But our identity now is going to say, does it work all the time? That's what we want to know. Does this work all the time? We can only do that by an identity. So let's go for it here. The sum formula for sine is going to give us sine of pi, cosine of the second angle, so it's the sine of the first angle, cosine of the second angle, plus cosine of the first angle times sine of the second angle. No need to simplify anything on the right hand side. But what is sine of pi? Sine of pi, sine of pi. Hey, isn't sine of pi really just 0? It's sine of 180 degrees. Times cosine of x. Cosine of pi is going to give you -1. So 0 times cosine is going to be simplified pretty good. 0, really on that side, subtract sine of x would give us exactly what we're looking for. On the right hand side, catching up a little bit here, it becomes this, which becomes this, which then at the end says these two are exactly the same. So you write QED. Okay, do you have to write QED? No. As long as I see the left-hand side and the right-hand side be exactly the same, you're good to go. So up until, like I told you, up until the 1970s, QED is what you had to put down. I'll just tell you it's a Latin phrase meaning something. And then also, all of a sudden about the 1970s, maybe because we didn't study Latin in school anymore, I guess, then they used to put like a little, small little box, like almost like a check box to say, hey, it was done. But I kind of like QED. All right, do you need to put it down on your homework assignments? No, you don't. All right, example problem here. Let's still think about the signs, the sum or difference formulas for sine, but let's use it in a different way. So here it is. Sometimes you will get this interesting pattern that happens here. You'll try to find the sine of 63 degrees. Then you'll try to find the cosine of 27 degrees. And as you're looking at it, you say, you know what? Isn't this really just the sum formula for sine? And if this is the sum formula for sine, how about if I just add these two angles together, see what I get? So we bring it down here, and you say, you know what? That fits this formula here from earlier. So I'm going to take the sine, the u, or the first angle, plus my second angle. When that happens is you get 63 plus 27 is 90. At that point, you can actually figure out the exact value of this weird looking expression at first, which really just becomes sine of 90, which really just becomes 1. All right. This is also for you guys to practice to sort of see the sum and different formulas from the other side. So here goes with our practice problem. So find the exact value of the sine of 43 degrees times cosine of 13 minus cosine of 43 degrees sine of 13. So yeah, those repeating angles sort of give it away. So I'll let you guys try it first. Go for it. So sine of 43, cosine 13 minus cosine of 43 sine 13. All right, that is really just going to be the difference formula for sine. And then at that point, then you say, oh, that's right, 43 minus 13 is 30. And then give me the value of sine of 30 degrees. Cool, 1/2 works, so it is 1/2. All right, getting just a little bit more complicated here. Let's talk about this here. So let sine of u be a negative 3/5, cosine of v being 12/13. Good. Okay, and angle u is going to be between pi and 3 pi over 2. At that point, I'll just sort of let you think about it. Remember, this is an example problem here from the textbook here, so it's all written out already. If you want to take a look at your textbook to follow along. Angle V is between 3 pi over 2 and 2 pi. So think about which angle value is there. And we're trying to find sine of u plus v. Well, our little problem is this. On the formula, remember, you're going to find the sine of u. You're going to have to also know the cosine of u. And so we're going to have to figure out what the cosine value is as well. So before we even start putting things into a problem here, we try to find the cosine of u. So cosine of u. And the book does it by identities. You know, you could do it that way. I like doing it by the unit circle. I think the unit circle is a little faster. So if you want to see it by identities, go for it. The identity between cosine and sine is this little Pythagorean theorem identity. Put it in a little different way. The minus sign comes out because it is in quadrant 3. And if you do that, you find out that cosine of u is negative 4/5. All right, do the same thing for the v. We know cosine of v, but we don't know what sine of v is. We use the relationship of the Pythagorean theorem between sine and cosine, simplifying, and we get ourselves sine of v. And now we have everything we need to punch this into the sum formula for sine. So sine of u plus v is going to be all this right here. We have already figured out each of those values here. Sine of u was given. Cosine of v was given. We had to find cosine of u. We had to find sine of v. And then again, simplifying, eventually stopping at negative 16/65. That would be the exact value. All right, our problem here. So the angles U and V in example 6. Can you find cosine of U plus V? Well, let's go back just a little bit here. Don't forget from the previous section here, sine of U is -3/5. That was where the angle was. Cosine of V was 12/13, and that's where the angle was for cosine. Or in this case, this was quadrant 3, quadrant 4. All right, let's go for it here. We're trying to figure out cosine of U plus V, and here's our formula. It's cosine of U, cosine V, sine of U, sine V. That's fine and dandy, except now we need to figure out, since we know cosine of U, since we know sine of U, we need to figure out cosine of U in order to plug into the formula. So this guy's going to be plugged into here, no problem. But we're sort of stuck right here. We need to know what cosine of U is. So I do it this way here. I know we're in quadrant 3. So we're going to wrap that around to the angle over there. That's angle U. And I'm going to get a coordinate here somehow. I know that sine is defined by the y value over the r value. So I can put those in already. R value is 5. The y coordinate is -3. All I just need to figure out is what x would be. And of course, I need the Pythagorean theorem to help me find that. Give you guys a little bit of time. Go for it. See if you can figure that yourself. All right, hopefully you had some time to do that. And here's what I got. Plugging in the -3 for the y value, 5 for the r value, simplifying it, x squared is equal to 16. Now we are in quadrant 4, so you know that x has to be a -4. And so this is what I have so far. I know what the cosine of U, I just figured that one out. Cosine of V was already given to me. I didn't need to do anything. That's 12/13. Sine of U was already given to me as well. That's -3/5. That's already given. So I'm still missing the sine of V. So it's the angle V over here, which corresponds to cosine V. So now I have to figure what this one is. So make ourselves a unit circle in a sense. We know we're in quadrant 4 because the angle measurement given. We know the x value is 12. The r value is 13. All yours to figure out the y value at this point. All right, plugging into a quadratic formula. We have ourselves -x squared 65 plus y squared equals to 13 squared. Squaring both of them, as we know, going to be 15/65 gets you y squared is equal to 25. Therefore, y equals to -5. Why is it a -5? Because we are in quadrant 63/65 is my final answer. I think I'm ready to put stuff in here. So that's going to be a -5/13 as y over r. Practice problem number 7. Now what we want to do is we want to verify more complicated identities. I know we did that before. I think we did that in 6.1. So now can we verify that this right here is an identity? Cosine of x plus y over sine x times sine y is equal to really cotangent x cotangent y minus 1. Okay, so I got to think about our rules here. I'm going to do this. I'm going to start off on the left-hand side because it's the more complicated side. I'm going to see if I can sort of get to the right-hand side. So think about what would be the equivalent form of cosine of x plus y. Write that out and see what you guys get. So according to the sum formula for cosine, it's going to be cosine of x, cosine of y minus sine of x, sine of y. And notice this part is still in the bottom here. All right, as far as algebra rules go, doesn't this mean that if you have a single term on the bottom, I can write this term underneath each of my numerator values? I think it says that. So let's move this over here. Let's move this, write it underneath here. So the first part, cosine x over cosine y, cosine x times cosine y over sine x sine y, minus, and then again on that side we have the same exact form over itself. All right, cosine over sine, that really is cotangent. So this really becomes cotangent of x times cotangent of y minus 1. And there it is. We've just proved that sort of weird identity, but it is an identity there. All right, then we have something called a reduction formulas for sine and cosine. All right, where's this sort of used at here is whenever you're stuck because you have a sine and a cosine at the same time. And usually you have square roots in there. You're sort of stuck into like what's really happening here. You can use this to simplify it out. So let's look at an example first. Here's a formula though. If you see something multiplying sine of x and then adding to something multiplying cosine of x, and you still want to simplify it some more, here's your simplification right here. It is going to be almost like if you think about it, it's going to be Pythagorean theorem of the numbers in front. Then you're going to multiply it times sine of x plus theta. And now the question is, for how does theta get into here when it wasn't present over here? Is the fact that we have values for it here. We can actually do this. We can say a divided by the square root of a squared plus b squared square root is going to give you cosine theta. So we'll see how that plays out. Okay, so here's what. Find an angle theta in radians and a real number a such that this happens here. So you got sine of x, subtract square root of 3 cosine x. We want to simplify this out as much as we can. We're going to do it by changing it into this form. So then you only have one trigonometric function. All right. How do we do this? First of all, we identify what's going to be the small a and the big A values here. So we have sine of x, so that means the a value technically is just a 1 that's over here in front. The b value is a negative square root of 3. And first of all, we plug into this formula here, the square root of a squared plus b squared. As we do that, we figure out that we finally get a 2. And theta is going to be the angle, standard position. That's at the point 1, negative 3. All right, the best way to do it, because you know the number or the values themselves, we're going to use tangent. Because notice, if you know your y value and your x value, you can just use tangent. And so if you do this here, you're going to use the inverse of tangent, which technically is inverse tangent of negative square root of 3 over 1. All right, if you do that, you wind up with a negative pi over 3. All right, so from beginning now, this is what we started off with. We figured out this is the answer here. And simplifying just a little bit here, notice now we have just one trig function. And we can graph this easily. We can solve this easily. And what we'll do in the next sort of sections here. Okay, let's practice here with this reduction formula. All right, changing it up just a little bit here, get a plus sign instead of a minus sign. That's really the major difference there. All right, let's go for it here. So labeling, A's are 1. It's the number in front of sine of x. B is the number in front of cosine of x. And we got this little formula for A. A is going to be the square of them, add it together, take a square root. If we do that here, plug it in, 1 squared is 1, square root of 3, squared is a 3, makes a 4, and the square root of 4 is a 2. Okay, got that, we're good there. Then we're going to have to use tangent to figure out the angle measurement. So B over A is going to be the value here. And if we do this, this gives us a square root of 3 over 1, or just square root of 3. And we should get tangent inverse of root of 3. And if we build it according to a unit circle here, first and foremost, we know we are in quadrant 1. All right, and if the x value is 1 and the y value is root 3, you know that the r value is 2. But what angle are you looking at when you do that? Well, if you want to, you can make it along the unit circle, because that's what we like to look at. So let's just do this. Let's divide everything through by 2. That makes the r value to be 1. So what angle measurement gives you an x value of 1/2 and a y value of root 3 over 2? And that's going to be pi over 3. All right, we found the angle measurement, and we found the real number A, so we're good there. So if you want to rewrite it, that would be equal to 2 sine of x plus pi over 3. There's your reduction formulas. We went from 2 trig functions, sine and cosine, down to 1 trig function. Practice problem number 8. It says, use the reduction formula to sketch a graph of this. Ooh, cool, okay. So again, pretty hard to sketch a graph of sine x plus square root of 3 cosine x. But if we convert it, and again, this is the exact same problem. In fact, it actually says on practice problem number 9, sketch 2 cycles of this. So back to practice problem number 8. We know the reduced form looks like this. Y is equal to 2 sine of x plus pi over 3. At that point, I think you should know what your amplitude is. All right, so amplitude is 2. What's your period? Period is the number that's in front of x that's multiplying everything together. In this case, if you look at here, that's just really a 1. So it's going to be period is 2 pi over 1, or just 2 pi. Now it does say sketch 2 cycles. So in this case, I'm going to go out to 4 pi, because that then will give me 2 full cycles. All right. And the phase shift. Phase shift would be the number in the back. It's opposite here. So it's plus pi over 3. Phase shift would take the opposite of this, divided by the number in front of x. Since that's 1, it stays as a negative pi over 3. Okay, so then that tells me how I should break this off into pieces. The amplitude tells me how high I should make these pieces. We good? So originally I went up to 4 pi, and I just sort of broke it up into 4, because knowing that there's going to be 2 cycles here. All right, now I can fill it in at least a little bit here. So pi over here, 2 pi over here. And I'm going to break this up into thirds. So because of that little phase shift here, I'm going to transfer a third of a pi. So really what I should do is I should break up these into 2 more pieces here. So there'll be 3 pieces here. Put two more tick marks here to make it 3 pieces. 3 pieces here, 3 pieces there. Okay, and I'm going to go a height of 2 here and a height of 2 down. So should look like this. If you want to label where the 3 pi would be, that's cool too. That's no problem. But notice what I did is I used the phase shift to help me sort of plan how many tick marks I need. All right, I got everything I think. Let's go with this. Let's put in dots for a regular sine curve that has an amplitude of 2 and a period of 2 pi. Can you put those in? What are the dots? So remember, sine is going to start here. By the time it gets to 2 pi, it should make 1 full revolution, right? So then it's going to have to go halfway about right here. It's going to go up to 2, down to pi at 0. About here would be, and here would be that. Okay, again, same thing here. It's going to come up here, come back down by this time. Go back down and then come back up. All right, those dots should be there. So the high values, the zeros, and the low values for sine. So again, technically it's doing this. Okay, now because the phase shift, all we want to do is we want to just scoot this a little bit here. So we're going to scoot it pi over 3. So we're going to scoot it back. The starting point of 0, 0 now becomes negative pi over 3, 0. All right, and this is a half, and we're going to need to use this much. That means this guy has to move just a little bit, but still in positive territory. So in that case, each one of those is going to have to do that. And I'm going to represent these by dots here, like this. I have blue dots. So notice everything is moved back pi over 3 units, especially the zeros. You can really see it with the zeros here. Just move back pi over 3 units. All right, I think we're ready for connecting. And we connect the dots. Again, a curvy line. Need to, and there are 2 cycles right there. All right, the practice problem here. I think I'm going to skip this one for now due to time constraints here. Work it out later. Let's look at the sum and difference identities for tangent. Okay, and again, just using the formula, knowing how to use the formula, that's all we're looking at. And we're going to just prove some identities using them. Write it down if you need to here. Open up your book. Maybe this should go on a 3x5 card somewhere. This would be pretty good. So let's go. So this is the example problem in the textbook here. It says, can you verify tangent of pi minus x is equal to the negative of tangent of x? And again, start off on the more complicated side, and you can work your way down. So complicated side, difference formula. Plugging in the tangent of pi, which technically is 0. And all that stuff goes away as zeros. Left with negative tangent of x. Our problem here, tangent of pi plus x. Well, that gives me tangent of x. What is this saying? Is that saying, can you prove that tangent has a period of pi? So notice, if you have an angle measurement, if you add pi to it, that means you came back to tangent. So really you're proving the fact that tangent has a period of pi. All right, let's go for it. Starting off with the more complicated side first. And can you give me the sum formula for tangent? Plug it in. Pi is your first angle, x is your second angle. All right, you should have it like this here. So tangent of pi plus tangent of x, 1 minus the opposite sign, then you multiply them together. All right, evaluating each of those here, and Everybody know what is tangent of pi? Alright, tangent of pi is 0, I believe. Then we have ourselves tangent of x at the end here. Then we got 1 minus tangent of pi again, that's 0, multiplying tangent of x. So if that's the case, on top I just have tangent of x. On the bottom I really just have a 1. In that case, I just proved my point. There it is, tangent. I just proved that tangent has a period of pi. That's cool. Alright, that's where we'll end today.